Hello! We are about to review the major concepts of our kinetics chapter. We will practice an instantaneous slope, an integrated rate law, the Arrhenius equation, and the fourth major topic, reaction mechanisms. In the first problem from our very first lesson, instantaneous slope, and the purpose of this really is to get us familiar in going with proficiency and speed in calculating an instantaneous slope of a line using our graphing calculators. The average rate of decomposition of nitrogen dioxide was given as a function of time. Into our first data column we have time going by in seconds, and into the second data column we have our reaction, where the reactant is being consumed and its measure of molarity is decreasing. We'd like to calculate an instantaneous rate at 75 seconds. So one of the things I first notice is that the time unit seconds indeed matches the list. That's a good thing. No conversions are necessary. And just show enough work that I know what you're doing. In other words, what is it that we are indeed graphing? Well, first of all, into my calculator, what I'll need to do is to enter some lists. And so with me, you're going to clear out anything that happens to be there. And into list 1, I want you to record the times. So just type those in: 0, 50, 100, 150, and 200. Into your list 2, type in the concentrations, NO2, as time goes by. 4.21 E negative 5, 2.8 E negative 5, 2.0 E negative 5, 1.4, and 1, all to the exponent of negative 5. And we have a matching concentration with the number of units of time. To calculate an instantaneous rate, what we'll need to do first is to find an exponential regression of list 1, list 2. So that's one of the first things I'll record, is showing enough work. Find the exponential regression. Choice 0, if you will, on your stat key. So stat, calc, skim down or type 0, exponential regression. We want list 1, list 2. And we'll get a screen. Now I don't need any of this information recorded. What I will need to do is to transfer it over to my y equals. And if you have anything there, just clear it out. Remember how to do this? We hit vars, choice 5, statistics, slide over to equations, and hit enter. And that carried the equation over. Make sure you check your window and you have enough data samples. I have 0 to 2000 for x. It's probably too large. I only need to go to 200. And the concentration units, very tiny actually, so 0 to 1 probably would be plenty of decimal places there. So I'm just making sure I have my windows in the correct area. Next thing I want to do is find the derivative, dy dx. And to do that, what we'll end up hitting is second function calc, choice 6, and we let our calculator think for a moment. And the time that we're solving for is 75 seconds, so I'll hit just 75 and enter. Notice that it comes up negative, but we ignore that. dy over dx, 1.717 times 10 to the negative 7th molarity per second. Maybe a little dot there, 1.717 E negative 7. And we found an instantaneous rate and the unit molarity per second. The second major topic we studied, the integrated rate law. The integrated rate law comes from our equation page. We had first order integrated rate law using natural logs, second order integrated rate law using reciprocals. In our problem, we have data that's provided for us in the first column, concentrations, and in the second column is time. Determine graphically if this is a first order or second order. Show enough work that I know what you're doing. So to show enough work, what we'll end up looking at If it's first order, the natural log of our concentration, N2O5, versus time. I want to see your slope of the line, and I want to see your correlation coefficient. And if indeed it's second order, it would be the reciprocal of our concentrations, N2O5 versus time. I want to see the slope of your line, and I want to see the correlation coefficient. That way I know what is the better straight line. So back to our lists, clear out what's there, and we have time must go in list 1 because that's going to be the x-axis. And the concentration will be in list 2. So don't let the order mess you up. Make sure that you press time into list 1. So into our first list, we're going to hit 0, 50, 100, 200, 300, and 400. List 2, 0.1, 0.707, 0.05. Oh, I missed this. It's 0.0707, 0.05, 0.025, 0.0125, 0.00625. There. Times 0 is 0.1, 0.707. I missed one right up here, darn it. 0.05, 0.025, 0.0125, 0.00625. I caught that because I didn't have the same number of entries in both lists, and we would get an error. So now what I'd like to do into list 3, I'll put my natural logs of list 2. So my cursor up here, natural log of list 2, and I have all of that entered in. And I'll do the same into list 4, 1 divided by list 2, and it will get me the reciprocals. Alrighty. Now we want to know the best straight line. So let's run our stat, calc, linear regression. And this time I want list 1, comma list 3, and I'm testing natural logs that way. And I'll record the slope of the line, 0.00693. And the r squared looks very good, doesn't it? 0.9999 repeating. Let's run exponential regression for list 1, comma list 4 and see what we get. Slope of the line, 0.3535. R squared, 0.888. Clearly, the best straight line, correlation coefficient closest to 1 is a first order. Remember that first orders have negative slopes. So I want to draw the best straight line here where the slope is the opposite of k. And therefore, remember the second order has a positive slope, and therefore it is not a straight line, so we'll just exaggerate that. So the best straight line is first order. This reaction is first order. The k constant we recorded. The k is the opposite sign of the slope. So k equal 0.00693. It's a first order, so 1 minus the overall order drops out molarity, and we're just left with a per second. Calculate the time required for the reactant to reach 0.045 molar. And so here, because we know it's first order, we go to our integrated rate law for first order reactions. The natural log of the concentration after time went by, 0.045, is equal to the opposite of k, 0.00693. We're solving for time, plus the natural log of the original concentration up here from the data table, 0.1. How long did it take for the original concentration, 0.1 molar, to degrade down to 0.045 molar? So now it's algebra. First of all, let's start with the right-hand side, the natural log of 0.045. Since I want to bring this side over, I'm going to subtract the natural log of 0.1. And I'll divide by the opposite of our k, dividing by negative 0.00693, and we'll solve for time. It took 115.2 seconds. Calculate the concentration left after 149 seconds elapsed. So now we'd like to know how much N2O5 remains after a certain time went by. So same equation, we just have a new target. The 149 is our time plus the natural log of the original value. So it's simplifying the right-hand side first. Negative 0.00693 times 149 plus the natural log of 0.1, and we get a value. I have negative 3.28. Remember that to get rid of the natural log, we would raise e to that value, negative 3.328. So opposite of natural log of our answer, and we have 0.035, we'll call that 0.036 molar units. A first order practice. Based on our graphing, we found a best straight line, letting us know what series of equations to use first order with respect to N2O5. In our third major topic, we talked about the Arrhenius equation. And on the back of our note-taking page, we have the Arrhenius equation, Kelvin temperatures. We have the non-graphing form and the graphing form of the Arrhenius equation. So here is the test-taking tool for this particular section. Let's take a peek at what it's asking. The gas phase reaction of methane and diatomic sulfur was studied at 550 Celsius. The relevant data was shown in the following table. The two different K constants, I can tell that it's second order, and I see the temperatures, but they are in Celsius. So let's right away make sure that we have Kelvin. 550 plus 273 is 823 Kelvin. And 625 plus 273, 898 Kelvin. Alrighty. Using the non-graphing form of the Arrhenius equation, solve for the activation energy. Well, the non-graphing form is given to us as the natural log of the ratio of rate constant 1 over rate constant 2 set equal to the activation energy over R, our gas constant 8.31, times the reciprocal difference of our Kelvin temperatures. Setting that into it, we have the natural log, let's call this K1, let's call that K2, of the reciprocal of 1.1 over 6.4, the ratio, equal to our target variable, EA, over 8.31, our gas constant, R, over the reciprocal value of T2 in a Kelvin, over T1. Let's simplify the right-hand side first. Natural log 1.1 divided by 6.4 equals. I'm going to multiply that by 8.31 to bring that side over. Alrighty. So kind of keeping in mind 8.31 has now been brought over. EA times this is equal to negative 14.633. Let's simplify what's in the parentheses. So we're going to divide that. We want to bring this over here. So we'll have some parentheses here. Divided by 1 over 898. Type that in correctly. Minus 1 divided by 823. Close your double parenthesis. we have our activation energy. Remember, that will come to us in a joule. So EA equals 144,202 joules, or 144.2 kilojoules. Take a look at this algebra and see how we solve for this. We have to be able to pull out EA. I simplified the right-hand side, multiplied it by 8.31, and then divided, using parentheses, I divided this, brought it over to find EA. What is the value of the rate constant at 600 Celsius? 600 Celsius. That's really saying 873 Kelvin units. So now our algebra is going to target a temperature. We're looking for a rate constant. Let's call this trial 1. So the natural log 1.1 over K2, that's what I'm solving for, equals, I know the activation energy, make sure we put that into a joule though, so 144,202, must keep it in the joules, over 8.31, times T2 now is 873 Kelvin, and T1 was our 823 Kelvin. 873 T2, looking for K2, so I'm matching those variables. 1.1 was at 823 Kelvin. Alrighty, so let's go to work and simplify the right-hand side. 144,202 divided by 8.31 times, I'm just going to use double parentheses, 1 divided by 873 minus, new set of parentheses, 1 divided by 823, close double parentheses there, and we get a value. Now remember, we need to get rid of the natural log sign, so this ln is the opposite, is second function ln is e raised to that answer. Alrighty, and I'm going to record this so far. We have 0.2989. Alrighty. And so that's equal to 1.1 over K2. That's where we are so far. All right, so how do we pull out K2? We're just going to switch those around. 1.1 divided by 0.2989. Alrighty, so those two really just switch places. 1.1 divided by our answer. Oops, I missed the divided by. Divided by the answer. And our K2 value, 3.68, and the unit molarity -1, second -1. Does that number make sense? It's a number that lies between 1.1 and 6.4, just as the temperature lied between 823 and 898. Our temperature was between those two values at 873. This number does indeed make sense. It's falling in the range that we were given. Pause the video if you need to practice that algebra. You need to be able to solve for EA, and you need to be able to pull out a rate constant. The Arrhenius equation also can be tackled graphically, and let's take a peek here. Given Kelvin temperatures and K constants, we're to use our graphing calculator, making an appropriate graph to determine the activation energy for the reaction. Show enough work so I know what you're doing. On your x-axis is the reciprocal of Kelvin temperatures, and on the y-axis is the natural log of K's. We hit a linear regression and find the slope of the line. The slope is equal to the opposite of EA over R. So let's go to work showing our graphs. We need to clear out some information. There I go. So into the x-axis, these are already in Kelvin, so that's nice. 338, 318, 298. I need those to be reciprocals, so on to list 1. I'm just going to go 1 divided by list 1, and I've converted those to reciprocals. Into list 2, I'm going to type the k constants, 0.0049, 0.0005, 0.000035. 1, 2, 3, 4. 1, 2, 3, 4 zeros. That's right. I need those to be natural log, so I'm going to put up my cursor on list 2, hit natural log of list 2, and let that convert over. So list 1 is the reciprocal of Kelvin temperatures. List 2 are the natural log of K. Let's run a linear regression, choice 4, of list 1, comma, list 2. And I'm going to record the slope of that line. Negative 12447.03. Alrighty. And r squared looks very good, doesn't it? Nice straight line there, as we would predict. So we run a linear regression. And find the slope. And the slope was given to us as negative 12447. However, the slope, recall, is equal to negative EA over R. And so we have one more step to do. We have to take the slope and multiply it by 8.31 to actually find the activation energy. So there's an additional step here. So EA is equal to, let's get rid of those negatives, 12447.03 times 8.31. Activation energy, obviously it's an energy barrier, so we know it will always be positive. Slope of the line times the R constant, and we find activation energy, 103,434.8 joules. 103.4 kilojoules. Again, practice this algebra so you become proficient and speedy. The last major topic, reaction mechanisms. One mechanism for the destruction of ozone in our upper atmosphere. Ozone, which is O3, plus NO, is in dynamic equilibrium with NO2 plus O2. That's the fast step. NO2 plus O goes on to make NO plus O2. That's the slow step. This is the rate determining step. What is the overall reaction? We're going to simply add the equation together and simplify, and I'll do my work over here. I have, let's see, I can probably do it right here, O3 plus, what else cancels? Here's NOs, they're going to cancel. NO2s cancel. And that's it. Yep. So I have NO is gone, NO2 is gone. So ozone strikes an oxygen atom, giving us 2 molecules of O2, and that works out to be balanced. What is a catalyst? The catalyst is something we start with and end with. A reactant in step 1, a product in step 2. NO is the catalyst. The intermediate is made in step 1 and consumed in step 2. The intermediate is NO2. The observed rate law comes from the slowest step. Let's begin by writing rate is equal to K, and it comes from K2, times NO2 times O. This is a bimolecular equation. However, we're not allowed to have an intermediate in our equation. So NO2 needs to be subbed out from the equilibrium above. That equilibrium arrow can simply be thought of as an equal sign. O3 times the concentration of NO is exactly equal to the concentration of NO2 times O2. We want to isolate NO2 by itself, don't we? We need to get this alone so that we can sub it out. So I'm going to divide both sides by the concentration of O2. And that's simplified. And now here is what I have to sub in for NO. So the observed rate law becomes rate is equal to K. And I'm not allowed to write NO2. Here's what I'm going to do. It's times the concentration of O3 times the concentration of NO times the concentration of O2, but see how that's under? So typically you'll see that to a -1 order, and I ran out of room here, times the concentration of O. That was originally part of our observed rate law. 1, 2, 3, 4 brackets in this observed rate law. Oxygen is raised to a -1 power because it was under. Although it's perfectly fine if you had written rate is equal to K, O3, NO, O, all over molecular oxygen. These indeed are the same, but you typically see it raised to a -1st power. So you can clearly see 4 ingredients in the rate law make it an impossible elementary reaction. The observed rate law comes from a step further down than step 1. We would never predict a rate, a mechanism to have 4 molecules colliding as the observed rate law shows. You've now completed one type of problem in each major area. Continue studying for your test.